let's start our next topic, continuity. One of the main applications of limits is to determine when a function is continuous. When you say a function f is continuous at x equals a, so we're talking about continuity at an x value if this is true. Let's write that again. If the limit as x approaches a of f of x equals f of a. Now you might be saying, well, hold on a second. Isn't that what we were doing when we were taking limits? We would plug in x equals a into f of x. Yeah, but remember, we couldn't do it all the time, right? Whenever we had a vertical asymptote, right, with infinite limits, we couldn't do it. Whenever we had an indeterminate form, we couldn't do it immediately, right? F was not defined at a. So there are plenty of times where a function is not continuous. Right, what I'd like to do is maybe get a graph going. And just maybe try to intuit when a function is continuous and when it's not. So let's start off with something like this. And keep drawing this. Maybe something like this. And we'll say this is y equals f of x. So we've got a couple of values of interest, a, b, c, d. Now that we've defined e, maybe we'll skip that. Let's go over to s, t, and u, let's just say. All right. So anyway, is f continuous at each of the following? So I'll put a check mark if the answer is yeah, or actually I won't say check mark, but let's just take a look at them, right? Maybe I'll use black, right? So the question, just looking at the graph, limit as x approaches a of f of x. Pretty sure that equals f of a, right? Because the hole is filled. All right. Now let's take a look at b. Right. F of b does not exist, right? I did not define f of b. And even if we did, the limit doesn't exist. Right? It equals negative infinity in this case, right? Because both sides go to negative infinity, but that does not exist. So f is not continuous at b. So I'll put an x. Oh, yeah. That looks like an actual x. Maybe I'll put a sad face. There you go. What about at c? Well, let's take a look. If we call this guy L right here, then the limit as x approaches c of f of x, well, from the left and from the right, it's clearly approaching the same thing, and that's L. But f of c is not defined, right? F of c does not exist. So f is not continuous at x equals c. Okay? Right, similar situation with d, right? If you take a look, here, maybe I'll use purple here. Limit as x approaches d of f of x, it definitely equals a value, but it does not equal f of d, right? F of d is down here, the limit is up here. So again, f is not continuous. I'll write a sad face every time it's not continuous, right? Don't do this on an exam, by the way. Similarly for f, right? The limit as x approaches s of f of x. Note that limit actually doesn't even exist here, right? Right, before, in these examples, the limit existed. They just didn't equal f of c or f of d. right? Here the limit doesn't actually exist because the left-hand limit differs from the right-hand limit, right? So f is not continuous at s because the limit doesn't even exist. This is called, so these two are called point discontinuities or removable discontinuities, whereas this is called a jump discontinuity. We'll get more into that in the guided practice. For t, same sort of thing. The limit as x approaches t of f of x does not exist. So again, not continuous. And last but not least, yeah, it looks like we've got a continuous function here. Even though the function behaves kind of weird, it's not smooth, it's not what we would call differentiable, but it turns out f is continuous. So the limit as x approaches u of f of x equals what is that? F of u. So here f is continuous at u. Okay. So let's take a look at this problem, right? We have a piecewise function. Now, this is basic enough that we can graph it. Now, remember exponential functions. Actually, I guess I'll stick with the pattern of using red for the axes and blue for the graph. Right, so here we have e to the x. Now, remember, exponential functions behave like this, and they would normally go like, right? But because we stop at 0, and in fact, it's not e to the x at 0, we write a little hole right there. And we should know that that value is 1, right? Because anything to the 0th power is 1, even if it's a weird number like e. Whereas x squared for x greater than or equal to 0, right? Well, normally that's a parabola like this, right? But if it's defined only for x greater than 0, well, it has the dot filled in, and then the parabola goes like that, right? So this is y equals f of x. Right, now, I think just looking at it, you can tell that it's continuous before 0, f is continuous after 0. The question is f continuous at 0? Well, let's take a look. The limit as x approaches 0 of f of x, well, I don't think that's too clear, right? Because f is defined differently before and after 0. So what we have to do is we have to look at the left and right-hand limits. And then make a judgment, right? See if they're equal and see if they equal f of 0. So I'll say look at the right-hand limits, left and right-hand limits, and f of 0. Right? This is very important. And f of 0. Don't forget about that. Right? So, limit as x approaches 0 from the left of f of x is the same as the limit as x approaches 0 from the left of, well, I guess before 0, f is defined to be e to the x, so that's what we're going to be looking at. And that's going to be 1. On the other hand, limit as x approaches 0 from the right of f of x is going to equal the limit as x approaches 0 from the right of x squared, right? Because to the right of 0, f of x equals x squared, right? Well, that winds up being 0, right? It's also worth noting that that's what f of 0 equals, right? Because f is defined at 0 to be x squared. Okay, but even though the right-hand limit equals f of 0, since the left and right-hand limits don't equal each other, that means that the limit as x approaches 0 of f of x does not exist. So f is not continuous at x equals 0. Okay. Now, colloquially, just based on what we've seen and what we've done, you might guess, and you'd be correct in the basic sense, that a function f is continuous at a if we don't need to lift our pencils when graphing f at x equals a. Oh, I guess I could just say, I guess I kind of type that in. Right. You don't have to lift their pencil. Okay. Now you might notice, okay, well, the definition of continuity is a limit, right? Showing that a certain kind of limit exists and that it equals the function as defined at the point, right? Showing that the limit exists shows that the hole exists. Showing that it equals f of a means we fill in the hole, right? So you might imagine we'll define left and right-hand continuity as well. So we can say a function f is continuous at x equals a from the left if limit as a approaches a from the left of f of x equals f of a. And, of course, analogously, f is continuous at x equals a from the right if, you guessed it, the right-hand limit at a equals f of a. So looking back at example 1, was our function continuous from the left at 0 or from the right at 0? Well, since the left-hand limit was 1, which does not equal f of 0, right, because f of 0 equals 0, then I think we would say no, f of x is not continuous from the left. However, because the right-hand limit did equal f of 0, we would say that f is continuous from the right. So let's just jot that down. So I'll say f is not continuous, I guess I like to say, let me just use that, at x equals 0 from the left, from the left. Why is that? Because the limit as x approaches 0 from the left of f of x equals 1, which does not equal f of 0, which equals 0. Meanwhile, f is continuous at x equals 0 from the right. Limit as x approaches 0 from the right. Of f of x equals 0, which does in fact equal f of 0. Okay, that's it. Now we'll get to a ton of practice problems where we're determining whether a function is continuous or discontinuous at various points. Piecewise functions in particular are something you have to watch out for. Like when we do the guided practice and then practice problems later. But let's get into a couple more abstract but very important ideas here. The same way we had limit laws and we kind of built up various limit ideas from them, we have continuity laws. If we have continuous functions f and g at a, like they're continuous at a point a, then so is their sum, their difference, multiplication by any constant, multiplication by each other, and of course division, assuming that we're not dividing by 0. Even function composition is continuous at a. So why is that helpful? Well, it means that if we know that the building blocks of a function are continuous, well, then the function is probably continuous as well. For example, if I asked, is this function continuous at 0? Maybe you could look at it and say yes or no. But what you could do is say, I guess you could say, let f of x equal, we just want to label this guy, equal sine of 8 pi x to the 5th minus 6x minus 1 all over 4x plus 2. So I guess you could say since g of x, which is a polynomial, right, this is this guy, and h of x, which we'll say equals 4x plus 2, maybe I'll lower that a little bit, are sums and products of continuous functions at x equals 0 g of n, or I should just say g and h are continuous at x equals 0. Since h of 0, which equals 4 times 0 plus 2, which equals 2, does not equal 0, we know by fact 2, maybe I should have said by fact 2 over here. We know by fact 2 that f of x, which equals, or maybe I guess I shouldn't say f of x yet. We know that g of x over h of x is continuous at x equals 0. Now, also, by fact 2, since sine is continuous at x equals 0, right? Sine's actually continuous at all x values. We know f of x, which equals sine of g of x over h of x, is continuous at x equals 0, right? So from these little baby building blocks of just polynomials and sine of x, well, we know that the quotient of the polynomials, right, that's got to be continuous. And then the composition, right, here's where the composition came into play. We know that there's a continuity going on there too, right? So this big complicated function, we know it's continuous without having to verify at every point, right? Without having to take this nasty limit, right? Now, we can talk about a function being continuous at a point, but a lot of times what we want to talk about is a function continuous on an interval? So we can say that a function f is continuous on the interval c to d. Remember, the brackets mean that the interval is closed, means we're including the endpoint. If f is continuous at x equals a for all a in the interval. Now, technically speaking, I need to be a little bit more careful. I need to say that, technically speaking, it means f is continuous on all a in the open interval and continuous at x equals c from the right and continuous at x equals d from the left, right? Because technically speaking, the endpoints, right, I can't go to the left of c or to the right of d. Technically speaking. If f is continuous on all real numbers, then we just say, I might say f is continuous everywhere. Or I might even just say that f is continuous. Right? Now let's look at one last problem. It's a little more advanced, right? For what value c is the function f of x equals blah continuous on all real numbers? So first we should note that since this is a polynomial and that's a polynomial, then f is going to be continuous everywhere except possibly at 2. So let's just note that since cx squared plus 2x and x cubed minus cx are polynomials, f is continuous on negative infinity to 2 union 2 to infinity, right? That means everywhere except all real numbers except 2. So we need to focus on when f is continuous at 2. So for what c is f continuous at x equals 2? Right? Because no matter what, for any value of c, they're going to be continuous everywhere else. F's going to be continuous everywhere else, all right? So what do we need? So I'll say i.e., when do we have that the limit as x approaches 2 of f of x equal to f of 2? Right? That's what we're looking for. Okay? Well, let's see. The limit as x approaches 2 of f, well, that's not a thing for a piecewise function. Let's break it up into the left and right-hand limits, right? This is going to equal the limit as x approaches 2 from the left of cx squared plus 2x, right? Because we're less than 2. And we can just take this limit, and we're going to get 4c plus 4. That's about as good as we can do for right now because we don't know what c is. The limit as x approaches 2 from the right of f of x. Thank you, Robert De Niro. Well, that's going to equal the limit as x approaches 2 from the right of x cubed minus cx. And that's going to equal 8 minus 2c. It's worth pointing out that since f is defined at 2, that this actually equals f of 2. All right? So for f to be continuous at 2, what do we need? We need 4c plus 4 to equal 8 minus 2c, right? Because we need the left-hand limit to equal the right-hand limit, which also equals f of 2, by the way. Well, you can just do some basic arithmetic and show that c equals, I believe it's 2/3. Let me just do it down here, right? You're going to get 6c equals 4, c equals 2/3. Okay? So just to be clear, let's just state our final answer crystal clear. So for c equals 2/3, f is continuous on all real numbers. Right, or in other words, f is just a continuous function. That's what we've got.